Very happy to have Tai, who is our current visitor. So Tai is a PhD student in geological engineering at Nanjing University in China. His research focuses on analyzing disturbance signals recorded by distributed acoustic sensing and quantifying the potential hazards they pose. He has particular experience in using data mining and machine learning techniques to process and interpret large sets of continuous waveform data from DAS. And so in this presentation, Tai will provide an overview of his past and some recent work in DAS technology and some of its practical applications, really trying to demonstrate how AI-driven DAS technology can enhance safety assessments in construction. Okay, so with that, over to you, Tai.
Thank you for your introduction. Yeah. Hello, everyone. Welcome to this talk. My name is Tai-Yin, and you can also call me Tai, D-I-D-E. I'm a PhD student of Nanjing University, and today I'm honored to present my work titled the Distributed Acoustic Sensing and Machine Learning for Engineering Event Detection. And let's start. First, introduction to DAS. What is the optic fiber? Every day, we need to use a fiber optic kit to communicate with each other. When we surfing the internet or making a phone call, the information have to transmitted through the cables, and the optical fibers is everywhere. It can be plotted on the ground, under the water, and under the and on the ground. So the cave can form a huge network all around the world. So and why we need to choose fiber optic to communicate? There are many advantages, such as cheaper, thinner, lighter, and less signal degradations, and can carry a lot of information, and with low power and non-flammable, flexible, and can transmit digital signals. The fiber optic lines are strings of pure glass as seen as a human hair that carry digital information over long distance, and the structure usually have 4 layers. The inner layers are cores and the claddings. Cores are made of pure silicon dioxide, and the photons can pass through the glass with minimal resistance, and the cladding is a glass sheet that surrounding the core. Like a mirror, it can reflect the light back into the core to reduce the light loss. And the external layers are butter and the jacket. They aim to protect to provide the physical protection to the fiber, and we can modify the buffer and the jacket layer to give the fiber some properties like the waterproofing, like the fire resisting. There are some examples of the different butter and the jackets. And what's the fiber optic scattering? The fiber cone contains oceans of impurities. So when the light passing through the impurities, the light will spread in all directions and create scattering light. And we focus on the backscattering light. According to different wavelengths, the backscattering can be divided into 3 categories: brain, Raman, and relay, named after the discoverers. And so, based on different backscattering principle, fiber will have different functions. Like brain scattering-based DSS can monitor string change of structures. And the Raman scattering is sensitive to the temperature change. And compared to the brain scattering and the Raman scattering, the Rayleigh scattering has a higher scattering coefficients, and this makes the is more suitable for measuring acoustic and dynamic signals. And this slide, I will introduce the basic concept of dust. When a pulse is sent into the optical fiber, it generates a phenomenon called the coherent Rayleigh effect. The dust interrogator continuously collects the return line parcels from different points along the fiber. And as the location of the disturbance, the intensity of the relay backscattering light changes. Look at this picture. As the vibration segment, the pink line's amplitude is changed. So by this way, we can determine the vibration position and the time. The dust system had two parts. First, is a dust IU interrogator unit. It can launch and receive the pulse. And the second part is a fiber. The fiber it does acts as a continuous liner microphones. So what's the characteristic of the dust? It's a high spectral resolution and the wide frequency band and the long monitoring distance. This table is a parameter. This is a specific parameter that we used. The maximum distance is 100 kilometer, and the maximum spectral resolution is 10 centimeter, and the frequency range is very wide, covering from infrasonic, sonic, and ultrasonic frequencies. And I also want to show you some applications of dust from the air to the sea. First, some research use the dust to monitor the geophysical signals produced by the capsule as it traveled at hypersonic speeds through the atmosphere. The dust interrogator reported an impulsive arrival with an extended code. And in the left figure, the inside code shows the zooms on secondary basis progressing along the cable after the initial arrivals. And another interesting application is use dust and presenting underground fiber optic to detect and check sounder-induced ground motions. These are three examples that dust ring observations of sounder-induced seismic events. This should show that dust can offer a new method of studying sounder-induced seismics, characterizing the near-surface velocity structure and probing the sounder-ground coupling process. And on the ground, the dust can monitor the urban basement construction. It's also called the near-surface seismic. The map is a development of the cave. The red line is the cave, and the box A donates a basement construction site. So we can analyze the dust signals and to make cross correlate grams before and after the excavations. And the black lines donate the peak travel time along the fiber cable. And we also can use the dust signals to estimate the velocity before and after the activations. We can see that at the west and the east of the basement, there are no significant changes of the velocity. But at the basement, there is a accurate velocity drop from 824 to 721. And we also can use that to monitor traffic signals. The right photo shows the multiplied vocal tracking recorded by dust arrays, and the right curves indicate vocals traveled by AI, tracked by AI algorithm. And the other research shows dust can use it for monitor the vibrations caused by motorcycle driving back and forth front here. And the dust coupled to examining subsea caves is also called dark fiber, allows observations of ocean and soil earth phenomena. This research is published in Science. They use a 20 kilometer long dust array to detect the seafloor force and ocean dynamics. This map shows the location. The pink line is the fiber optic cave, and during the several days monitoring, they found the dust can detect the seafloor fault zones, induce secondary micro-size generation, host low tide points, storm-induced sediment transport, and infragravity waves, and even the breaking inertial waves. And dust can also use for wildlife monitoring. Dust can record the sound of whales, and we can use the data to estimate the 3D position of the sound of the whale for animal density estimation. And we also can use the sound of the whale to make the full passive seismic recording for subsurface exploration. When the sound of the whale spread to the seabed, it can reflect to the fiber, and we can use some geophysical methods to analyze the signal, and then we can rebuild the structure of the seabed. In summary, I think our work is just like the investor chopper. We use the dust to monitor oceans of vibrations. In recent years, the studies most focus on the field of geophysicals. And my work is to use the dust to the field of engineering construction. I want to listen to the infrastructures vibrations like drilling, rockfall, excavation, and some water leakage. My work can be divided into two parts. The first part is the design of dust optical caves, and the second part is to build a signal identification model by the machine learning. First, the cable design. I want to explore how the tightness of the optical fiber affect the signal quality, because the tight buffered cable amplifies the connect to the local environment, And a very loose tube is poorly coupled to stream by responsive to temperatures. So which one is better? We don't know. So we do this. We conduct a test to explore the fiber stream and the dust amplitude response. These test devices can be divided into three parts. The first part is the dust IU. The frequency is 5,000 hertz, and the wavelength is 0.5 meter. And the second part is the linear slide table and the cable. And the cable we use is single mode fiber with a total length of 200 meters, and the test section is 2 meters. And at the end of the fiber, we use the gills to fix to the linear slide table. And the linear slide table can change, and the linear slide table can progressively increase the string until it changes 16,000 microstrings with different speeds. And the third part is vibration source to generate vibration signals with different frequency and different amplitude. And that is the result. This figure is a relationship between dust amplitude and the fiber string at 4 frequency. You can see the dust amplitude peaked when the fiber was in the loose state, and when the cable started to tension, the amplitude first decreased rapidly and then slowly, and eventually stabilized as the string increased further. The left figure is curves of dust amplitude versus fiber string fit with the exponential function at variable signal frequencies. And then we draw the correlationship between the characteristic dust amplitude parameters and the vibration signal amplitude. We can see that the string effect weakened as the vibration intensity increase. So we can draw a conclusion that when we tighten a tape, will result in a decrease in the amplitude and the sensitivity of dust. And when loosening the fiber can enhance the dust amplitude response. But the loosening layout can increase the friction between the cable and the structure. Is very harmful to the cable protection. So we need to keep a balance between the sensitivity and the survival. We designed a twin tension optical cable to improve the monitor performance. And this part I will introduce the AI-based dust solution for vibration identification. There are two challenges. First is the data size, and second is AI classification algorithm. First, the data size. The collection of the engineering events in the real world is very difficult. I want to show you some pictures and videos of collecting signals in the real world. This video is to collect the excavation signals in the tunnel. We can see the air condition is very terrible, and because of it, half of the time our DOS interrogator cannot work. And every day my shoes were full of mud. And in the wild, the rain and the wind can stop our monitoring. And we often don't have space to eat, don't have toilet, or even don't have food. When we monitor in high altitude area in winter, there is no road for cars, and we need to overcome the oxygen lacks, and it's very cold in the mountain, so we need to wear mask to fight against the extra cold. Although I went to many places to collect the vibrations, the number of data is still not enough to build a data set. So to solve the problem, I try to combine the on-site test with numerical simulations. We use DEM, and the software we use is the MetaDem. It's developed by the Professor Chun Liu. And there are 4 steps to create a vibration. First, stacking model, then focus on units and unit moving, and the last, the microscope vibration. We also use the elastic cloud model to establish the vibration signals. And we use the damping boundary to eliminate the most of the boundary functions energy. By the way, we constructed some models in MetDam based on real-world conditions. There is an example of the hammer. This figure is a real signal, and the figure below is a simulated signal. We can see the 2 signals is similar. It have some similarities, but because the simulation occurs in an ideal environmental with slowly signal attenuation, so the tail waves are longer compared to the real signals. This slide presents the simulated signals under different hammer heights and different bar depths of the optical fiber. This slide shows the simulated signals at different hammering frequencies and the simulated signals at different acceleration speeds and back waves. This slide compares the real Rockfall signal with simulated ones. By this way, we can expand the amount of the vibration samples, providing a robust data set for AI model training. And next, we combine the example machine learning method with us to build an automatic event in identification system. There are 4 parts. The first part is anomaly detection, and the second part is the data size. The next is the picture selection, and the next is the classification. And my work is focused on the last part, aiming to improve the classification algorithms accuracy and computational efficiency. So I use transfer learning methods to transfer the speech recognition model to the dust identification model, such as the CNN, multitask learning, JN, and HMM, and RiseNight, and JN, VJJ. There is another challenge, is the new class identification. For example, we train our model with 10 classes, but if there is a unlabeled 11 class occurs, the model will mistakenly recognize the new class as the existing 10 classes. So to solve this problem, we present an improved offsite recognition method. When the new class occurs, the model can automatically detect and report the new class. But to be honest, by this way, the recognition accuracy will have a slight decrease. And I also want to show you a real-world application of the proposed method. We have developed a computer vision-based and machine learning-based monitoring system, the system to classify the wire break events in pipes. And the first, this is the wire break signals, and this is a computer vision method to detect the signal, and then use the machine learning method to classify the signal. There are some results. This shows that our models can classify the vibrations with high performance. And the green one is wire break signals, is separate with other signals. And we can draw the conclusion. First, dust can be effectively used for engineering events detection. And then cable design can have a huge impact on what you want to monitor. So we need to keep the balance between the monitor performance and the cable survivals. And finally, AI-based DAS opens the door to a greater range of measurement opportunities. And thank you for your attention.